Good afternoon, everyone. I'm Xiang, and on behalf of the Kernel Evolve team at Meta, I'm excited to present Kernel Evolve, scaling agentic kernel coding for heterogeneous AI accelerators. This is joint work led by Gang, Carole, and myself, and the broader Kernel Evolve team. The three of us will walk you through the problem, the system, and where this is heading. Let's set the stage. Every day, Meta serves trillions of requests across more than 1,500 distinct models on a heterogeneous hardware fleet. NVIDIA, AMD, and on MTI silicon and the CPUs. Underneath every one of the requests is a kernel, a small program that translates the high-level model operations into the specific instructions a chip can run efficiently. Kernels are the last mile from model to silicon, and because kernel efficiency directly drives both our total cost of ownership and the revenue, getting them right matters enormously. But every new chip or model means those kernels have to be rewritten and returned. So here's a core problem. The number of kernels we need doesn't scale linearly. It grows as a product of the three factors. First, hardware heterogeneity, different memory hierarchies, ISAs, and execution models. For example, MTI alone went through 4 generations in 2 years, and the kernel tuned for 1 generation underperforms on the next. Second, model architecture. We have gone from DLRM to sequence models to LM scale ranking models to generative models. Each add operators the previous never needed. Third, kernel diversity. Vendor libraries covers operators such as gem and convolution, but there is a long tail of custom ops such as feature preprocessing, customized attention kernels, fuse operations with low library implementation. Multiplying by those together, and you will get thousands of unique kernel configurations. Hand tuning by expert simply doesn't scale. So why existing approach can't close the gap? There are two popular existing approaches, each with its own problems. First approach is the AI compiler approach. AI compiler is a popular approach in spite of many advantages, such as faster compilation speed with good enough out-of-the-box performance. It alone has its many limitations. For example, compilers falls behind on new hardware features and the new model architectures. Thus, compiler-generated kernels frequently fall short on absolute performance. Second approach is a human-in-the-loop, one-shot or few-shot agentic approach. Most people nowadays use tools such as Cloud Code or Codex in an interactive-only mode to write kernels. While it aligns with the AI native dev flow, the human-in-the-loop nature makes the human becomes a bottleneck in finding the optimal solution. Besides, the bare minimum functionalities provided by the code agent lack systematic way to accumulate knowledge and data that enables cross-node learning, cross-session learning, and in the future post-training. So that leaves one core question. Can we develop an autonomous self-evolving kernel agent that can beat state-of-art kernel implementations by human experts across a heterogeneous hardware? To answer that, I'll hand over to my colleague Gang to talk about our proposed solution, KernelEvolve.
Thanks, Xiang. I'll walk you through how KernelEvolve actually works. At its core, KernelEvolve reframes kernel optimization as three things working together: a graph-based search over kernel candidates, retrieval-augmented prompting, and a persistent knowledge base. On the right is a for loop. A user prompt becomes a task description that sets an outer loop tree search. Each node in the tree is a kernel candidate: green node for good kernel, red for buggy. For each node, a inner loop runs. It retrieves hardware-specific scales from the knowledge base and synthesizes a dynamic prompt at runtime, then sending prompts to a LLM backend, including Cloud Code, Codex, or our own agentic models. These kind of models author kernels in different DSL, Triton, CuDA, MTI AC++, and even more. And those kernel candidates are evaluated on real hardware, MTIA, NVIDIA, AMD, and CPU. The diagnostics feedback to the next round in the tree. Let me unpack this as a three-pillar: search, knowledge, evaluation. Pillar 1 is search. The outer loop is a state machine that decides what to explore next by selecting frontier node from a persistent graph. This strategy is configurable from one shot to linear to greedy to MCTS to evolutionary algorithm, increasing in graph complexity as you can see along the bottom. The fitness function is simply speed up over PyTorch with one hard constraint. Any kernel that fails correctness gets a fitness of 0. So the search can be aggressive about performance because correctness is never negotiable. Unlike a standard assistant that try a few generations, we explore hundreds of candidates and let execution feedback guide the search. Pillar 2, and this is the part I would most like you to remember, is the knowledge base. The challenge is that MTIA is meta-owning AI chips, so it's absent from any public LLM training data. Ask a bare model for a MTIA kernel, it will emit GPU-flavored Triton, and that won't even compile on MTIA. We solve this with a hierarchical knowledge base which includes hardware constraint and guidance organized per kernel target. A deep search sub-agent retrieves the right document based on the providing feedbacks. For MTIA, it can retrieve, for example, SFU component and lab device mapping, cross-P communication, dual-core execution, warp specialization. The model effectively learns the hardware at the inference time. Semantic way, onboarding a new chip becomes injecting document, not retraining a model. Pillar 3 is what makes this production grade, the evaluation harness. We unify a stack of profilers, Triton bench for correctness and speed up, PyTorch profiler, NCU, Proton, and MTI Insight, plus our own MPP for low overhead instruction level signal. Evaluation runs as a function as service workload, which decouples kernel generation from evaluation on AI accelerators. And when a kernel misbehaves, we can emit C++ and replay it in seconds for faster agentic debugs. This is the difference between an agent that writes a plausible code and the one you can trust in production. Every candidate is correctness validated with safe fallback. So does it work? Correct first. On kernel bench, the Stanford suite, we pass 100% across 3 difficulty levels and across 480 configurations, including 160 18 operators times 3 hardware platform, including H100, MI350, and MTIA. We are 100% numerically correct, verified with touch.o close function. This figure shows fitness improving as the search progress. Our principle, prove coverage before we talking about speed up. Now we can talk about speed up. Across production workloads, KernelEvolve delivers 1.25 to 17x. A few highlights. Vanilla attention in ANAMA 3.1 at 4.6x, convolution 1D at 6.5x, and MTIA training MRS norm backward at 17x. This span compute bound, memory bound, and custom operators, and develop cost drops from weeks of expert effort to hours of automatic search. Now let's look at the same operators across hardware platform. This chart shows the convolution 1D and convolution 2D. Identical chips, same operator, run on 5 different architectures: A100, H100, MI300, MI350, and MTIA. Two things stand out. First, KernelEvolve wins on every platform. It's not turned to one vendor. Convolution 1D gets 1.77x on A100, 2.3x on H100, 2.64 on MI300, and 6.54x on MTIA, where the knowledge base does the heavy lifting, because the LLM has never seen MTIA code in training. Second, the relative gains shift across different AI hardware. Convolution 2D peaks at 4.71x on MTIA rather than AMD and GPU, showing that the search adapts to each chip's bottleneck, not a one-size-fits-all optimization. My takeaway: one system, five architectures, no per platform engineering. Where does this speed up come from? Take Convolution 1D as an example. PyTorch 2.0 launches 5 separate kernels, including expensive layout transforms, even we are using Torch.compile. KernelEvolve discovers a fusion into just 2 kernels, emulating the redundant memory traffic. And it does this across different AI hardwares. One more point on MTIA for pre-processing operator. This isn't just optimization, it's enablement. If PyTorch has no native kernel and fallback to CPU, KernelEvolve provides a owning on-device path. With that, I will hand it to Carole for where this is heading.
Thank you, Gon. So Gon has shown you the whole kernel evolve system and how it's achieving 1.25 to 17 times speed up and also 100% correctness coverage for kernels that we have in production models. Next, I want to close our talk with something that we didn't expect and what we actually learned from the kernel evolve framework about Meta's own hardware design. Because Meta's Training and Inference Accelerator, or MTIA, is not part of the Frontier LLM's training corpus, we're pretty impressed by what KernelEvolve-an is able to discover. Their discovery is purely through exploration from the design space. And what this means is that what KernelEvolve-an find as a workaround are genuine signals about the hardware microarchitecture features. Here are 2 examples that I want to share with you that highlights this capability and how it has shaped our next generation silicon design. First is that the KernelEvolve-an search can consistently figure out how to maximize circular buffer depths. And this is telling us the per PE local storage size was the bounding constraint on DMA compute overlap. And how we're using the signal is to then increase the local storage size from 512 kilobyte to the 1 megabyte region for our next generation chip design. Second is the Conv1D operator example. What we found is that the KernelEvolve-an kept on converging on two-phase scratch pad buffer workaround because the hardware is lacking a inter-PE sharing primitives. And this has motivated us to add a hardware native row-wide reduction feature. And we find this to be a pretty interesting lesson in the way that a KernelEvolve-an can repeatedly discover these workarounds for the hardware that it has access to. And it's inspiring us as computer architects on what to prioritize for in terms of design feature. And we're pretty excited about this also as a future direction in the sense that this seems to be a scalable co-design methodology between computer architect and also AI agents in designing next generation hardware. Looking forward, there are 5 key directions that I want to put on your radar. First is that while we have shown you pretty impressive capabilities from KernelEvolve framework that's focused on individual operator optimization, I think this is just the first step. We have this tremendous opportunity to move beyond the single operator scope to look at whole model optimization. And sort of the milestones that we are at is to figure out opportunities across layer fusion and how to translate those optimization into end-to-end graph. Second is that we expect new abstraction boundary to be defined for code generations in general. Today, we are deploying KernelEvolve framework in the PyTorch operator Triton abstraction layer. But you can imagine that a very similar idea can be applicable to other abstraction layers that's at the lower of the system stack, including, say, MLIR to PTX, or even if we have access to SAS instruction, for example, we could also take a look at how coding agents is able to generate SAS code. And this is exposing an interesting design space trade-off between, I guess, the size of the design space, the search budget that we are willing to spend on code generation, and also the quality of generated code in terms of performance, efficiency, and cost. There's also interesting research opportunities on how global resource optimization can be done across heterogeneous ISA for performance and energy trade-off. If you are more in the machine learning side of design space, reinforcement learning from execution feedback is also a pretty interesting topic to go figure out how to adapt frontier model to learn proprietary silicon without exposing all the sort of business critical design component. Finally, beyond accelerating deployment speed and maximizing kernel performance, we now have all the essential building blocks that allow us to treat efficiency and sustainability as a first-class optimization objective. And this is an area that's dear to my heart, and I hope that more is able to leverage the kernel coding capabilities to actually look at how to translate a lot of these work into efficiency optimization and look at the sustainability angle as well. Here, if we can make AI to be more efficient, it will directly translate to lower operational energy and operational cost, and higher utilization of AI hardware will amortize capex as well as embody carbon. Our North Star here is to enable fully automated hardware-aware code generation across Meta's whole AI stack, and that will have to cover both NVIDIA and AMD GPUs as well as Meta's own custom silicon MTIA. But then there's also pretty interesting space when we extend beyond accelerator and start looking at CPUs as well. To wrap up, there are three important takeaways that I want you to bring with you. First is that kernel coverage is a deployment gate, and the KernelEvolve framework that we talk about here has been demonstrated to provide these capabilities automatically. Second is that KernelEvolve agentic search come with this knowledge injection that can produce production-grade kernels already, even for proprietary hardware that the frontier model may have never seen. Finally, we demonstrate how our KernelEvolve framework has already come with pretty impressive speed up for kernels that can run 1.25 to 17 times faster. And on top of that, we also show how it's already achieving 100% correctness coverage using the both external open source benchmark as well as some of our internal benchmarks. And what this means is that we can now generate kernels for our ranking and recommendation models faster and have these faster and more efficient model to serve the inferences in production today. The idea that I want to leave you with for our talk here is that while we've shown you all the capabilities that KernelEvolve coding agent is able to do, what I want you to remember is that these agents do not just write kernels for our own hardware. They are all these inspirations that we are getting from the kernel evolve agents. As computer architect, I thought it was pretty interesting and inspiring about what they discover and how that's telling us what hardware to build next. Thanks so much for your attention. I hope you'll come and to our talk during the conference, and we can discuss more on this space. Thanks.